The last section that we're going to talk about together is Chapter 12, Section 8, Probability of Compound Events. We're going to move along and fill in the blanks, and if we have time, maybe we can do the got it when we get to class together. If you find the probability in this example up here that the next song is both a rock song and also a song by an artist whose name begins with letter A, this is an example of a compound event. Which consists of two or more events linked by the words and or the word or. So you're looking for two items. One of your essential understandings today is that you can write probability of a compound event as an expression involving probabilities or simpler events. This may make the compound event easier to find. And now we got a lot of vocab, let's make it through. When two events have no outcomes in common, so the outcomes have nothing that have to do with each other, the events are mutually exclusive. M-U-T-U-A-L-L-Y. Mutually exclusive when the two events have no outcomes in common. If A and B, describing events, are mutually exclusive events, then A and B is always 0 because you can't have them together. When the events have at least one outcome in common, they are overlapping events. We'll apply these as we move along in our examples, but for right now we got to get our vocab down. You need to be able to determine whether two events A and B are mutually exclusive before you can find the probability of A or B. Okay, so up here they're dealing with this word and. Down here they're talking about the word or. Moving on. How do you find the probability of events that are mutually exclusive? Well, if it's a word or, you add your options together. Okay? If you're talking about the probability of events that overlap, let's say now we have the or word. Okay, this is all about the word or. If two things may equal each other, like they overlap, you are going to subtract the probability of A, you're going to take the probability of A and the probability of B, just like you did up here, but then you need to subtract where they overlap. Let's apply this in a couple of examples. Suppose you spin a spinner that has 20 equal-sized sections, and those sections are numbered 1 through 20. What is the probability that you spin a 2 or a 5? Okay, well, we need to just kind of acknowledge, since 2 and 5 are not the same, this is what we call a mutually exclusive event. They can never equal each other. So what we do is we take the probability of spinning a 2 and we add the probability of spinning a 5. And this again is because they are mutually exclusive and we have the word or separating them. So the probability of spinning a 2 is a 1 out of 20. The probability of spinning a 5 is 1 out of 20. When you add, you get 2 out of 20, which is equivalent to 1 out of 10. So in this one, we simply add our options together. Let's look at this again. Suppose you spin a spinner. It has 20 equal-sized sections, and they are numbered from 1 to 20. What is the probability that you spin a number that is a multiple of 2 or a multiple of 5? So what I'm going to do here is I'm going to write down my multiples of 2. I'm going to write down my multiples of 5. And I'm also going to put a star here that I'm going to put a little, well, let's find our multiples first and then I'll tell you what our star will be. On our spinner, the multiples of 2 are 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of these guys. Now let's think about your multiples of 5. 5, 10, 15, 20. There are 4 of these guys. Now, because this time, I'm sorry these are so close to each other, because this time I can have an overlap, this is an overlapping problem. What are the ones that overlap? Well, the items that overlap are, well, just look at the ones that are the same. 10 and 20. Because both 10 and 20 are a multiple of 2 and a multiple of 5. So I'm going to say there's 2 that overlap. So because this is an overlap problem, I need to follow my rule from down here. Overlapping events. I take the probability and I add them up. So, excuse me, the probability of a 2 is 10 out of 20. Plus the probability of 5, well, how many did we just say that was? 4 out of 20. But this time, because there's an overlap, I have to subtract my overlap. So minus 2 over 20. Because it overlaps. Okay? So 10 plus 4 is 14. 14 minus 2 is 12. So that gives me 12 out of 20, which reduces to 3 out of 5. Okay, so we talked about one at the top. This one was not an overlap problem. This one down here did have an overlap. So make sure you understand the difference between something that doesn't and something that does. Let's try the got it. Suppose you roll a standard number cube. What is the probability that you roll an even or a number less than 4? I'm thinking in my head of all the evens. And I know that's 2, 4, and 6. And now I need the numbers that are less than 4. So 3, 2, and 1. I notice that I do have an overlap, but let's first say, okay, there's 3 items here, there's 3 items here, but I have an overlap, and the number that overlaps is the 2, so that's 1 item that overlaps. See the 2 that overlaps? So I say the probability of an even was 3 out of 6, plus the probability of less than 4 is 3 out of 6, minus the overlap, which is 1 out of 6, equals 3 plus 3 is 6, minus 1 is 5 out of 6. Let's do part B. So this one was an overlap problem. What is the probability that you roll a 2 or an odd? Well, this is not an overlap. The reason is that 2 is never odd. So you simply add your options together. So your probability of 2 plus your probability of odd. Let's see, there's 1 out of 6 on a number die that are 2. There are 3 out of 6 that are odd. That makes 4 out of 6 total, which reduces to 2 out of 3. So in this one, the top one was an overlap. This one is not an overlap. We're going to talk about now independent events. Independent events are 2 events, and let's see, 2 events are independent events. independent, E-N-T at the end, not A-N-T, independent events if the occurrence of one item doesn't even affect at all the probability of the second event. So when they don't relate, like you're not saying like, oh, they're both on the same number cube, or yada, yada, yada. When they have nothing to do with one another, we multiply our options of independent events. Let's look at problem 2. Suppose you roll a red number on a cube and a blue number, a red number cube and a blue number cube. What is the probability that you roll a 3 on the red and an even on the blue? So you have 2 rolls. One does not affect the other. In other words, just because you roll a 4 on the first one doesn't mean you're going to roll a 4 on the second one. They're independent from one another. One won't change the other. So we're going to take the probability, we'll talk about the red one first, okay? We'll take the probability on the red one, they want us to get a 3. And this time we multiply by the probability, we're talking about the blue one, and we need an even on the blue. Since they're independent, that means you multiply your options together. Okay, they're two totally different number die. So the probability on the red one is a 1 out of 6, times the probability on the even is a 3 out of 6, because there are 3 even numbers. 1 times 3 is 3, and here's where people might get mixed up. You don't leave this as 6, because 6 times 6 is 36, which reduces to 1 out of 12. So there's a 1 in 12 chance that you're going to get a 3 and then an even. Got it. You roll a red one, you roll a blue one. They don't affect each other, so it's independent. What is the probability that you roll a 5 on the red and a 1 or 2 on the blue? Okay, so let's talk about the red one, and then let's talk about the blue one. They're totally separate from each other, so we multiply our options together. So the first one, I want a 5. The second one, I want a 1 or a 2. Well, the probability of getting a 5 is a 1 out of 6, and the probability of getting a 1 or a 2 is 2 out of 6, because you got 2 options, 1 or 2. 1 times 2 is 2. 6 times 6 is 36. That reduces to 1 out of 18. Moving on.